Okay, wait ah. Okay. Oops. Okay, so for this afternoon class, we are going to look at the example for beam number 2. So for the example beam number 1, I will send you the recorded video. Okay, so I hope at least you can go through with me a few examples. Okay, maybe there will be one more, I hope. Okay, if successfully. Okay, on the tutorial, the video recorded for tomorrow, my tomorrow class. Okay, so of course I will welcome all like Zul to ask me question. If you yeah you start somewhere or you cannot follow, and you must always let me know so that I can be slower at some parts. Okay, okay, without any delay, I will start on this, explaining how to solve this beam problem number 2. Okay, can you see my screen? Example 2.
Yes.
Okay, so thank you. You can refer to the documents. If you think that soft copy is difficult for you, maybe you need to print out, or probably you redo the example. Okay, as what I have request my previous class to do. Okay, the remaining class, please yeah, redo the example. Okay, so let's have understand this problem. Okay, here we have two span of beam. Okay, let me highlight my reading. Okay, so and then we have field loading. We have 15 kilonewton. We have UDL 3 kilonewton per meter, and we have 50 kilonewton meter. Okay, so this will be considered later under our Q or Q naught. Okay, I will explain one by one. So today we'll be covering the whole, process of the stiffness method. Okay, so given EI is constant here, given you a value, E is 200 gigapascal, I is 206 power 6 mm power 4. So meaning that you need to always know how the ways to convert, okay, Pascal, convert mm4, okay, to we are going to use the unit kilonewton and also meter, okay, in solving this problem. So, and then what is our problem? We want to determine the magnitude and direction. Direction of rotation, meaning that either clockwise, counterclockwise, clockwise. Magnitude means the number, the value. Okay, so at B and C. So meaning that this is referring to unknown displacement or unconstrained DOF. Okay, be aware of these terms. Then we need to solve also for internal member forces. So it is not support reaction, but internal member forces for member BC only. So what does that mean? Internal member forces. You'll be talking about shear force and also bending moment. Okay, so but it also give make the problem complicated. Okay, so it said that support A has settled some value, okay, of this value, meaning that this A, the displacement, if there is no such case, it should be equal to 0. But now for question B, displacement at this A equal to negative 2 over EI. Okay, let's have a look. So I actually like to explain step by step, okay, so that it seems like a guideline to you, okay, to start off. But after all, I found that students start to follow exactly, okay, they already fix their mind, oh, I must do this step 1, I must do that step 2. So I think it is not a good idea. So please, okay, ignore my steps, okay, because Of course, you will always start with notation, but after all, you can gather any inputs as you like, as long as you can form or establish the load and displacement relations. Okay, so now what I would like to share with you is how to give a notation to nodes, element, and also the DOF. Okay, so for the nodes, if you still remember my lesson earlier, we put the nodes at support, or there is any difference in terms of EI or EA, but in this case we have only EI. Okay, so but the EI is constant here, therefore we put the nodes at the support only. So we have support A, we have support B, C, therefore we put node at A, B, C. So in between these nodes will be the element. So you park the element 1 and 2. So element we put in the box, node we put in the circle. Okay, this will be similar for the frame, composite structure, and also for truss. And don't forget to draw the arrow, because this arrow will identify where is the near end and where is the far end. Okay, so this arrow, the beginning of the arrow is the near end, I, and the end of the arrow will be the, the nodes will be the J. So B will be the far end for element 1, and A will be the near end for element 1. Okay, this will be used later. Okay, then you need to know that for beam, there will be 2 DOF per node. And the DOF must be this one only for 2D, dealing with the vertical and also a rotation. Okay, so at each of the node, you need to place this DOF, okay, arrow. So that is why at node 1, you have placed this arrow, if you can see that, this arrow. Okay, at node 2 as well, at node 3 as well. And these are the positive sign. Okay, so next will be the Zul questions to me just now. How to give a numbering to this DOF? So we need to number. The rule is number. This rule is only applicable for when you are doing manual calculation, because it will be more easier for you. Okay, in programming we don't apply this rule. There will be just follow the naming from XYZ, from near end and to far end XYZ. They will be following this naming for all the elements. Okay, because the computer cannot sort out something like this like a human. Okay, you need to give a very clear instruction. Okay, from near end to far end XYZ. So they will just follow. Okay, but now since we are having a manual calculation, we need to sort it out so that it will make our life easier. Okay, so number the DOF, number the unknown displacement first, then the known displacement. So it will be a bit time if we want to know which one is unknown, but it will be more easier for us to know which is the known. So let us identify what is the known displacement. So it will associate with the support reaction. For example, we know that this is about the support reaction. So we are referring to the DOF only. Of course, we have AX, right? But yeah, it's not in the DOF. So and BY and CY. So other than that are the unknown. Okay, so or maybe I make it more clearer here. Okay, this one, the A at Y direction, we know that is equal to 0. The rotation at A, we also know that it is equal to 0. Okay, and this delta BY also equal to 0. And CY is equal to 0. Okay, so you no need to show me this, but you need to know. Okay, so once we have identified this is known, we number the unknown first. Which one will be the unknown? I found my this. Okay, I can change color. So this unknown, this unknown. Okay, the one I drawn in blue color is unknown. So therefore I name it first. So I can name this 1, 2, or if you want to name this number 2 as 1, no problem. Okay, so we name the unknown. Later is named the known. So meaning that 3, 4, 5, 6 are known. So I will write here so that you are getting 3, 4, 5, 6 are all equal to 0. They are known. Okay, the unknown is only D1 and D2 only. Okay, so any question from you? Okay, I will move to the member stiffness matrix. Okay, so member stiffness matrix, you will follow this template. Okay, I have to circle to you. You are going to determine the 12 EI over L cubed, 6 EI over L squared, 4 EI over L, and 2 EI over L. Okay, the remaining are only repetitive. Okay, and it is stated here, symmetrical. So you no need to determine for every items. You just determine these 4. Okay, and you need to know that we are preparing this member stiffness matrix is for global axis. Okay, at global. Okay, so how we do that? There are 2 elements in your problem, so we do one by one. Okay, so for member 1, this one. Okay, so you have the L is 6 meter and 2 meter. Okay, 6 meter. And for element 2 is 2 meter. So what you can do is just putting in the E, the I. Okay, now we are using unit kilonewton and meter. Make sure everything is in these units. And the L is 6 meter. So this is how you find the 4 items here. 12 EI, 6 EI, 4 EI, 2 EI. Once you have formed this done, just place it into the template. Okay, for example, let us place some of the input. For example, let us put this 12 EI over L cubed, 2400. Where is the locations? K11. So it means that you are placing at the K11. So let me try on more, maybe this one. K13, sorry, K23. So it is 6 EI over L squared. So 6 EI is this one. Okay, I put a square, 7,200. Therefore, I put a negative 7,200 according to the template. Okay, so I hope you are clear on how to get the member stiffness matrix. Just follow the template and determine the elements in this matrix. Then you need to name this numbering. Okay, the numbering is following these rules. Okay, you need to follow naming the near end first. Okay, in this beam, we have vertical and also the rotation. So you name the Y direction first, then only the Z direction. Therefore, here you can start with NY, then you name NZ. N means near end. Then you go to far end at the Y and the far end at the Z. F is far end. So then from this element 1, can you try? Yeah, the answer is given to you. 4, 3, 5, 2, why is like that? So it means that you look at this 4 is near end Y. This 3 is near end Z. So you name accordingly. And then 5 is far end Y. And this 2 is far end Z. Are you okay, class?
Yeah.
Yes.
Okay, thank you. So you do it the same for member 2. But if member 2 having the same EI, having the same length, so you no need to redo it. You can directly use these elements in the K1. Okay, you can exactly K1 equal to K2 equal to this matrix. Okay, only the naming for this will be different later. Okay, so let us have a look on element number 2. So we do it again. Okay, 12 EI over L cubed, 4 EI over L squared, sorry, 6, 4 EI over L, and 2 EI over L. So for this time, element 2, the length is 2 meter. Okay, just put this in the equations. Okay, then you get a set of new elements. Just pop it in again to the template, and then let's have a look on this numbering. Okay, this numbering is very important. If you done this wrong, you done the structure stiffness metric wrongly. Okay, so let us have a look. It must be from the, sorry, I need to highlight many times. This is NY, this is NZ, this is FY, this is FZ. Okay, from the near end, we have 5 and 2. Okay, so then we can form the structure stiffness matrix. So just now what we have prepared is member. So if there are 10 members, you have 10 member stiffness matrix. When you want to solve for the problem, you need to gather all the member stiffness matrix into the structure stiffness matrix. So here I highlight. Now you are looking at the structure. How it will be different here. The K symbol K is in capital letter, if you can see that, and it will be the combination or summing up all the member stiffness matrix. How to do that? Okay, so I have gather all the K1 and K2 here. Okay, maybe let us try again. Okay, I think we have done this in our last lesson. Okay, so let's have a look on the one that I highlighted in the square. Okay, if you can see that, if I want to find K22, okay, meaning that I'm following to look at column number 2 and row number 2. Okay, therefore for K1, I'm referring to column at 2 and row number 2. Okay, so I take note on this figure to add 0, 0. Then I go to K2 and search whether it has column number 2 and row number 2. Yes, okay, I also find it. Okay, and I take note this at 6400. So to get my structure stiffness metric, this element K22, I just sum this up. This one, sum with this one. Okay, so means that you need to determine the remaining of these elements in this matrix. This is very time consuming actually. Okay, so read the question properly. I mean, if you are being evaluated or the problems given, if they do not require you to determine the structure stiffness matrix, we don't actually need to determine all of this. Okay, we just determine whenever will be used. Okay, to solve for the problem. Okay, but I have to show you all of this. Okay, at least you have a feeling of how to establish the structure stiffness matrix. Okay, maybe we can go another one. Okay, the one that is happening at K2, maybe not happening to K1. Let's say K11. Okay, So let's say K11. So meaning that you are referring to column number 1 and row number 1. So if you found that K1, there is no column number 1 and row number 1. So meaning that there is no inputs from K1. So you move to K2. Okay, then you found that there is a column number 1, row number 1. This one. So you can directly place this to K11. Okay, so this is how the structure stiffness being formed. Before I proceed, if you have any question for me?
No, madam.
Okay, so I will,
No.
yeah, thank you. So I will move on to the load displacement matrix. I think I write wrongly here. Can you help me to change it to vectors? Okay, so these are vectors. Yeah, you can do this first. Once you have give the notation, you can already determine the load and displacement vector. Okay, so if you still remember just now, we know that 1 and 2 are unknown, right? Therefore, we name them first. So they also, you can put this information into the displacement vector. Okay, where you put D1, D2, they are unknown. Okay, the 3, 4, 5, 6, okay, we know the value equal to 0. Okay, so this is how you write a displacement vector. Okay, and then how about Q, the load vector, or sometimes they call a force vector. What is that about? Okay, so this Q, okay, just to remind you again, is for support reaction, oops, or the loading. Okay, I must add one more in front. Nodal means that the loading is acting at the nodes. Okay, class, may I know which loading is acting on the nodes?
Three kilonewton.
One.
Yeah, you're please referring to this problem. Again, I can't hear you well. So any loading acting on the nodes, and what is the value?
Not 3 kilonewton.
I can't hear you well. I don't know who is
50.
50. Yeah, is it? You are talking
Yes,
about
50
Okay, okay,
kilonewton.
okay. Thank you. Yes, the nodes here you refer to this DOF. Okay, so we have this 50 is acting at the nodes. Okay, and 3 kilonewton per meter and 15 kilonewton is acting on the element, not acting on the node. Okay, so they will be the inputs in our they got 1, 2, 3, 4, 5, 6. So you refer to this number lah. It match number 2. Okay, so you just put at the number 2, 50. Why positive? Because it is acting exactly like our positive. This is the positive sign. Okay, so the rest Q3, 4, 5, 6 are the support reaction. If you recheck here, 3 support reaction, 4 is AY, 5 is BY, 6 is CY. Yeah, they are all support reaction. Okay, I want to test you. What if I have a loading 20. This is only I add just to test you. So 20 kilonewton. Can I know what happened to my Q? Anyone to try? If I have a 20 kilonewton acting at C,
It becomes 20
at where?
Q1,
Uh,
Q,
CY.
Q3, Q3,
Q6.
Q6, yes, you are right, because
Q6.
this arrow following the 6 is matched on this direction, 6
Six
direction,
arrow.
vertical. Okay, so Q6 will have a value of 20 kilonewton. Positive or negative?
Negative.
Thank you, negative. Do we still have Q6?
No.
You sure? When
No,
I
we don't have Q6.
yeah, when I ask whether it has Q6 means that is there has a CY value. The CY value is still there, right? The support reaction is still there. So, but topping up, there is 22.
Yeah.
Yeah. Therefore, in this case, you have this Q6 minus 20 for this, I mean, this element of this vector. Q6 minus 20 will be the answer. Okay, I hope you understand that, because the question will not always referring
Which is
to the,
we didn't know the Q6, right?
sorry.
We didn't know the Q6, so that's why we need to do like that, Q6 minus 20.
Because there is Q6 at this problem. And the Q6 we don't know. You are right. Okay? So Q6 is the support reaction and also loading. Okay? So now if you have seen that we have find all the inputs for vector Q and D. If you notice that I have put a line here. Maybe they call this a partition. Okay, so we can actually, if you refer this partition, okay, you can actually divide the unknown and the known for the displacement and the support reaction. Q, I mean the force vector. Okay, you will always double check. This D unknown will be always opposite with the Q unknown, opposite. And this D known will be always opposite with the Q known, okay, by this partition. So if you recheck, yeah, it's correct, then I mean, I think everything will be fine. Okay, always recheck that. Okay, so next is this Q naught due to the intermediate loading. What we need to, if you still remember the fundamental of this stiffness method is they shall not have any loading on the element, but we have loading 3 kilonewton per meter and 15 kilonewton on our element 1. Okay, the strategy to get rid or remove this loading is to transfer them in term and determine in terms of fixed end reaction. Means that this is the one that we are referring. Sorry. Okay. If you can see my arrow, these are the fixed end reaction that we want to determine. So for example, in this case, there are two loads. So you need to this method of superposition. You need to get the loading, combine both of these loadings. So let us start with this 15 kilonewton. Okay, to get the 15 kilonewton, you can refer to this case 1 here. Okay, this template is given to you. Case 1, case 2 are given to you in the appendix. Just refer to that. Okay, and find the appropriate case. Okay, but before that, I would like to go back to refer our numbering of element 1. Okay, our element 1, the numbering is 4, 3, 5, 2. Okay, so therefore we name it here 4, 3, 5, 2. Accordingly, only we add the knot at the back because this is due to the intermediate loadings. Okay, let's start with case 1. 15 kilonewton is the P. So to get the moments, we use PL over F. Okay, so Q3 knot and Q2 knot, okay, will be dealing with moment. Okay, PL over F. If you can see that, PL over F is here. PL over F is here. Okay, so let us put in the PL over 8 inside. The P will be 15, L is 6 meter and divide by 8. Okay, then maybe you will ask why this is negative, why this is positive here. This is because of this direction. Okay, this negative is because at B, okay, at B, the assumption of this moment is counterclockwise. Okay, but in this case, they put it in the clockwise. Therefore, it will become positive. When you opposite it, so the negative will change also to positive. So this is why my answer to this. Okay, then you need to also determine the vertical reaction, RA and RB, which is associated with the Q4 knot and also Q5 knot. So P over 2. So this will be the P over 2 here. So P is 15, 2. Okay, divided by 2. So you settled with case 1. You can move to case 2. I change my pen. Okay, let's see, purple. So now case 2, the loading is exactly like case 2. Okay, there is very good. Okay, so we can directly use the template. Okay, what if the W is not at the left side but at the right side? Anyone? Can we still use this? I mean, exactly this MA, MB, RA, and RB? Any idea?
No?
Yes, no. Okay, is no. But we can modify them. Okay, so meaning that this W now, if it is like this, okay, so if in the face-to-face, I will ask the students to actually turn their paper, means that you just mirror it, okay? The moments just, imagine you have a printout of this case 2, then you just turn it at the, look at the back page, okay? You will find that this MA will be here, okay, and this MB will be at here. Okay, so similarly, you can write MA is actually 5WL squared over 192. MB now will be becoming 11 WL squared over 192. But the direction is still the same, therefore MB will be negative here. So RA and RB still the same. No, it's different also. Terbalik, it's different. So RA will be, sorry, because it's not similar. RA will be 3WL over 32, and RB will be, I cannot write more, WL over 32. Okay, so it just mirror it. Okay, you will see that the moments, we can still use the value here. All right, so let us try to solve for case 2 for this 3 kilonewton per meter. So now the moments, we have Q3 knot and Q2 knot for the moments, Q4 knot and Q5 knot for the vertical reaction. So let's try with Q3 naught. 11 WL squared over 192 is here. Okay, just put in the W, 3 kilonewton per meter. The length here is 6 meter. That's all. Okay, that's what you do. Okay, and the Q2 naught is now 5 WL squared over 192. So this is the one that you're supposed to have a look on this. Okay, so and then for 13 WL over 32. Okay, and 3 WL over 32. So you just need to sum up this effect. Okay, of course, you need to consider the direction as well. Okay, so after all, you are going to put this Q naught value into the, in the methods of this structural form. Okay, where the matrix here is size 1 times 6. How to do that? You just write number 1 to 6. Okay, then fill in. Like for example, Q2 naught is 14.06. Okay, 14.06 here. Why negative? Because this is clockwise. Remember, our positive sign is this one. Okay, then Q3 naught, okay, is from 17.44. Q4 naught is from 14.81. And Q5 naught is from 9.19. There is no Q1 naught, there is no Q6 naught, equal to 0. Okay, class, you have any question for me for this?
No.
Okay, so I will continue putting the global stiffness equation. Okay, now we are into solving it. Okay. So let me put this. Okay, before I go to the global stiffness equation, okay, I would like to write the full things, okay, concept for it. Q equal to K D plus Q naught. Okay, this is a stiffness equation or load displacement relations. Okay, we are going to put in the vectors and the matrix that we have determined earlier. Okay, arrange it in such. Okay, for example, for Q, you have determined the Q earlier. Okay, and you have until 6. Okay, and then the K, you also have determined the structure stiffness matrix. Okay, 6 times 6. And you also determine the displacement vector. Okay, 1, 2, 3, 4, 5, 6. And you also determine the Q naught. Okay, so you just place it properly, okay, to solve your displacement. Okay, let me write here. So you have Q, you have K, you have D, you have Q naught. Okay, and we know that there are 2 unknown displacement in this case. Okay, so you can do a partition. Okay, so I'm going to do a partition here. So I know that this is D unknown here. Okay, and opposite it, it must be Q unknown here at the bottom. And D unknown can be partitioned with another, this is D known. And this D known opposite it will be the Q known. Okay, so remember that the stiffness matrix must be a square matrix. Okay, so therefore this, if you have already partitioned it 1, 2 here, so you have another partition 1 and 2 here, 3, 4, 5, 6 will be here. Okay, so if you refer my notes earlier in the PPT, okay, in our previous class. We have actually divided this structure stiffness matrix into four region. Okay, if I give a name, okay, here, okay, to make our explanation easier. So this part, let's say, is K11. This part, let's say, is K12. This part is K21. And this part is K22, let's say. So now we can solve the unknown displacement. After you arrange your this stiffness relations, your first aims is to solve. Okay, unknown displacement. Okay, how to solve the unknown displacement? We need to establish a simultaneous equation. Okay, you can see that you can get this equation out. K11 multiplied DUK plus K12 multiplied DK. This is how you multiply the matrix and the vector. Okay, if you are confused already right now, let me put a laser here. So I want to solve this DUK. Okay, so the one that I actually do is I write an equations based on QK equal to K11, the elements in this K11 region, multiply with DK, okay, plus the elements in the K12 region, multiply with DK, okay, then plus Q0. So from this, you can solve for DUK, the unknown displacement, D1 and D2. Okay, so if you refer back to your known displacement, your D3, D4 to D6 are all equal to 0, right? So when K12 multiply 0, this is 0. So the remaining are K11, DUK plus Q0. That's all. Okay, so what I would like to highlight here actually is just now you have determined the K 6 times 6, right? So it is very time consuming, especially if you having a limited time. Okay, if the problem do not request you to find the structure stiffness matrix, you only find this 4 value will do. No need to find all the elements, no need. Only to find this the one that I highlight in purple. Why? Because these are K11 region. Okay, only the K11 region, okay, will give you answer here. Do you understand what I mean, class?
Yes.
All right, very good. Okay.
Yes.
So now, in this here, K11 is this these 4 items only. So that is why here, if you see your documents, you only show this. Okay, instead of 6 times 6 matrix, you only show this. So I hope now you can see a solution to D. Okay, either you put it in the matrix form, directly solve it using your calculator, or you solve it based on these 2 simultaneous equation. Okay, maybe we need to check, okay, whether you know how to form this equilibrium, simultaneous equation from this matrix. So the 0 is from okay, this 0 is from here, 0. H6400D1 is from H6400 multiply D1 plus 43200 multiply D2. Okay, before ending, we need to plus Q0, 0. Okay, then it forms the equation number 1. Okay, for equation number 2, 50 equal to, now we look at the row number 2. So it will be 43200 multiply D1 plus 115200 multiply D2. And then plus negative 14.06. Okay, then this is the equation 2. Then solving this equation 1 and 2, you solve for D1 and D2. And you must know what is the meaning of D1 and D2. If you forget, you need to go back to where is our numbering. So D1 is talking about rotation at C, and D2 is talking about rotation at B. Okay, so therefore here you can see that D1 rotation at C, okay, is negative 3.44. Okay, is counterclockwise. Why? Because you got a negative value. Okay, and D2 is a rotation at B, and it is positive, therefore it is clockwise. And you must remember that you are measuring rotation, so the unit must be in radian. Okay, if you are measuring vertical or horizontal displacement, so your unit will be in meter. Okay, class?
Okay.
Okay, thank you. Yeah, all right. So, but in this question, we don't show how to get the support reaction. Okay, so you can refer my yeah, before I ask you to refer, maybe I will write it here. Okay, using this, after solving the unknown, if requested, okay, you can solve for the Q, support reaction, unknown, or any of the internal forces, okay, unknown. Of course, it is unknown. Okay, so now Q, U, K unknown will be referring to this part. Okay, will be equal to, following the row, it will be K21 multiply DUK plus K22 multiply DK. Okay, but now this is no more DUK. You already find the answer. Okay, so you just multiply with that answer. Okay, for example, you are referring K21 is here. So meaning that this 0 multiply D1, there will be a D1, D2 that you already found answer. X, Y, let's say. So it will be 0 multiply X plus 14400 multiply Y. Okay, and then plus Q naught. Then you got your Q value. Of course, it might be not that clear through this example because it's not shown, but the recorded video sent to you later has shown you how to determine the support reaction. In this problem, we are we wish to determine the internal forces. Where? I forgot. Dekat mana? I forgot the question. Let me check that. Determine for member BC. Okay, internal member force for member BC. Okay, so let's see. Member BC adalah is the element number 2. Okay, but they give you a problem. They said support A now settle vertically 20 over EI. Okay, meaning that D6, as earlier we have known that support A is deal with D6. Okay, this D6 has a value of this one. Okay, after you substitute the E and I value. Okay, so D6, D4, D6. I think I confused. Let me see. Support A. So support A is here. It's not D6. Support A vertical displacement is still with number 4. Okay, so it will be talking about 4, D4. Okay, D4 will have this value, but negative because settlement is going down. Okay, so that is why you have a D4 equal to this value, negative of this value. Okay, so meaning that we have D1, D2, and also D4. Okay, but D4 is known. It is not unknown. It's non-value. Okay, so the process of calculating is still the same. Only we need to require column number 4 in your structure stiffness matrix. Remember, earlier we do not put in this K1, 2 is because D3 to D6 are 0. When K1, 2 multiply dk will be equal to 0. But now the dk has one value here. Okay, and it is associated with this 4. Okay, number 4. So you need to get a column number 4 also from the structure stiffness matrix. Okay, for you to multiply with this D4. Okay, let's have a look. Okay, everything, the remaining everything are the same, only because of this D4, existence of D4, you need to recalculate the D1 and D2. Because support A settlement and support A not settled, the D1 and D2 are different. Okay, so let's see. Okay, so let's do the equation. So the first equation will be 0 equal to H6400 multiply D1 plus 43200 multiply D2 plus 0 multiply negative 4.6 power negative 4. Okay, plus 0, Q1 naught. Okay, so this will be your equation number 1. The equation number 2 will be 50 equal to 43200 multiply D1 plus 115200 multiply D2 plus 7200 multiply D4. Okay, and then minus 14.06, equation number 2. So you solve these two simultaneous equation, you solve for the new D1 and D2. Okay, and this D1 and D2 can help us to determine the member force at BC. Okay. This 5261, wait, be patient with me. I think I shall put it this way. Okay, so now we are referring to only element number 2, which is 5261. Okay, so when you are determining the member force, we still use the stiffness equation. Just now we use Q equal to KD plus Q naught, all big capital letter, which also means at the global axis. But now we are talking about local axis, and every information is happening at local axis. So everything will be putting in the small letter. Okay, so if you can see that we have Q. How to name this Q? You'll be naming from 5 to 6 1. Okay, Q5261. And then for the K, member stiffness matrix for element number 2, which means this will be the K2. Where you get the K2? You have determined earlier, right? Can I move? This one. Okay, you take exactly everything. This K2. Okay? Okay, K2. Then the D will be following this numbering as well. 5261. So this D will be the displacement that you have determined, okay, at global. Okay, so it will be D5, D2, D6, and D1. Okay, so you have determined the D1 and D2 here. So you can put this D1 and D2 into this vector D1, D2. And 5 and 6 are initially 0. Okay, so you just put it 0 here. And how about Q0? You need to get the Q0 from the the intermediate loading. Associate with element 2 only. Okay, so let us go back 5 to 6 1. Okay. Here. Okay. So it will be this one. 5, 2. Okay, you can get this value, okay, to the, oops, here. Okay, following this will be the Q5 node, Q2 node, Q6 node, and Q1 node. Okay, so once you have formed this local stiffness equation, but you don't need to find all, you just need to, why? Well, 5, 2, 6, 1, 5, 2, 6, 1, 5, 2, incomplete lah, this question. I mean this answer. There will be another answer as well. You need to also find Q6 and also Q1. Okay, maybe you can top up your answer later in your documents. Okay, because you want to find all the member forces at BC. Okay, so it will be all the 5, 2, 6 ones. But here it shows how to get the Q5 and Q2. The Q5 will be the shear force at B. Okay, if you're referring to number 5, it is vertical. So we talk about shear force. And then Q2 is talk about moment. So it is at MB. Okay, so how to do that? So let us have a look on the pen. So you can put it Q5 equal to 64800 multiply 0. 64800 multiply 7.2 power negative 4 plus negative 64800 multiply 0 and then plus 64800 multiply negative 3.6 power negative 4 and then plus Q0, Q5 naught 9.19. So now you will get your VB, the shear force, directly, okay, from the stiffness method. So no need to find the bending equation, solving for the axial cut section for axial or shear forces. You can directly, okay, obtain this information. But if you notice that you are obtaining the information at the node, the nodes only. Okay, the way where you place the DOF. Okay, the one that you don't put, you cannot find it. So still, either you put a note there to find the answer, or you use, the analysis that you have learned in chapter 1, okay, to solve it, because it is already determinate. Many of these you already solved for it. Okay, class. I think my sharing session today, complete. Do you have any question for me? Maybe I will stop recording first.